Hi everyone, my name is Fei Yang Jiang, and today I will be introducing DFS, which is a classic algorithm for graph theory. So, what is a DFS? It's basically a traversal algorithm people use to explore a graph. And how it works is that you pick a node to get started, and you would follow one path until you cannot go any deeper on that path. Then you would backtrack to the most recent crossroad that allows you to go to another unvisited direction. And then you will continue on that direction until you cannot reach anymore. And then you repeat the process of going back and then visit another unvisited direction. So without further ado, let's jump into an example to see how it works in practice. So let's see this example on the right. We have the procedural code on the left for us to refer to. For this example, let's assume we start at node A. We mark this as the starting point, and let's mark this as visited. And what are the neighbors of A? We have B, D, and C. Let's assume we go by the order from smallest to largest when we have tons of nodes to visit. So all three nodes are unvisited at this point. So we can go to node B here, and we mark it as visited. What are the neighbors of B? We have A and D, but only D is unvisited. So let's go to D next and mark D as visited. So at this point, all the neighbors of D are already visited. So that means we need to backtrack to the last crossroad that still has unvisited node left. So let's go to B. Does B have any unvisited node? No. So let's go one step down to A. And does A have any remaining unvisited node? Yes, it does. It has node C that's still unvisited. So let's go to node C here and mark it as visited. And for the unvisited neighbor of C, we have node E. And at this point, for E, we don't have any unvisited neighbors. And that means we need to backtrack, right? So we would backtrack to C. And C does not have any unvisited neighbors as well. So let's backtrack to A. And A does not have any remaining nodes, neighbors that are unvisited. So that means since A is our starting point, we cannot backtrack anymore. And that means we have traversed the entire graph and we finished. So let's take a look at the runtime complexity of this algorithm. So first, we would have the first step, which is marking the node as visited, and that is just constant time operation. Let's mark this as constant. And then for the for loop, so for each node U, this would loop through all the neighbors you have. And say here, if we have a node A, we have three neighbors, right? So the degree would be 3. And the same thing go with D or B. So basically, this step is proportional to the degree of the node we're currently at. And then because if the neighbor is not visited, we would call DFS, which is basically mark it as visited and explore its neighbor. So if we look at the entire picture, that means we visit every node exactly once. So this part will give us big O of V, with V just being the number of vertex we have in the graph. And since we're visiting every node once, and we visit every node's neighbor exactly once, that means basically we call like degree U on every node, and that will give us in total, it's just summing of the U at degree U, and that is basically proportional to the number of edges we have. You can count from this example if it helps better. But basically, if we add those two parts up, that gives us a total of V plus E big O runtime. And that is just linear. Okay, so it is a very efficient algorithm and we can use it for multiple purposes. For example, the most basic ones, we have 1, 0. We can use it to traverse through a graph and find the connected components in the graph. For here, we have only one connected component, but if we say we have another node F here connected to a node G somehow, and once we call a DFS on node A, we still have those two to be unvisited. And once we start from either of those two nodes, that will give us another connected components, and basically we can find how many connected components there are in the graph. Another use of this algorithm is that we can use it in topological sorting, and we can also use it to find connectivity between nodes. So basically, all the nodes within the same connected components are connected through the starting node. So that means we have a path between them. So there are tons of ways that we can apply this algorithm to graph problems, and it's a very useful algorithm to keep in mind. So thank you for listening, and that's it about DFS.